Bismillahirrahmanirrahim. We'll continue our discussion on main memory management in this lecture. In previous lecture, we have discussed dynamic partitioning. So in this lecture, we will proceed for the same dynamic partitioning and discuss the placement strategies for dynamic partitioning. We will also see what are different types of addresses and how logical to physical address translation takes place in memory. So let's proceed. We continue with the placement algorithms with dynamic partitions in this lecture. What are the process placement strategies with dynamic partitioning? Here the placement of a process in memory is done using a suitable technique that can induce less use of compaction, since we have already said that compaction is an expensive and time-consuming method. So there are three placement strategies available for dynamic partitioning: best fit, first fit, and next fit. In best fit, the smallest size of partition that can accommodate a process and creates no or very small hole is selected. While in first fit, the memory is searched right from the beginning or top to find the first available partition that can hold the process. Here, the holes may be created little bigger. Last strategy is next fit, and here search for a pre-partition is done from location where previous or last process was placed. Hence, we would require to search half of the memory. But again, first available hole after previous placement will be selected, and the hole created may be little more bigger. As you can see in the figure, we apply the three placement strategies now as an example. A process of 16 KB needs to be placed in memory. The gray colored partitions are the occupied partitions, while the spaces in white are the available partitions where we can place 16 KB process. So according to best fit policy, operating system needs to search a free partition of exact size of the process, that is 16 KB or little higher, so that the holes may be created very small. So here you can see the 18 KB slot is appropriate for 16 KB process. Let me highlight it. So 18 KB partition is good enough and a hole of 2 KB is created. Now, if we have to use first fit placement policy, so the operating system would first find the empty slot of size big enough to hold 16 KB process right from the top or beginning of the process of the memory, and it would find a 22 KB slot. Let me highlight it. This is the 22 KB first found slot, and a process is placed there where a hole of 6 KB is created after placing 16 KB process there. Now, if operating system selects next fit strategy, so it would have to look for the previous placement first. The previous placement is this one. You can see the previous placement location. This is the previous placement location. So in figure, you can see previous process placement position with the name last allocated block. So search for the free big enough partition will start from next location after this last allocated block. So search would start from here towards bottom. A free partition of 36 KB is found at the end. You can see this is the free partition. So the process will be placed here. "36 KB is big enough to hold 16 KB process, but at the risk of creating a big hole of 20 KB. Hence, next fit placement strategy wastes more space as compared to first fit and best fit. Next fit strategy generally locates blocks towards the end of the memory, as you have seen previously, while first fit generates blocks towards the beginning of the memory, and they create small size holes as compared to the next fit. While the efficient strategy is best fit, that tends to find exact size of the partition or the one big enough to hold a process with intention to create very small holes. But even whatever strategy you apply, still the holes will be created ultimately. An operating system has to initiate compaction very often. Now, if all the processes in memory are blocked, a new process needs to be loaded. So, operating system has to choose among blocked processes a single process that has to be replaced with a new process. So, the selected block process will be swapped out to virtual memory and new process will be loaded at its place. The replacement algorithms will be discussed in coming chapters. How relocation of processes is done in memory. Due to swapping and compaction, a process keeps on changing its memory location. And this is the reason physical addresses of processes are never fixed. We now need to learn about different types of addresses and differentiate among them, especially the logical and physical addresses. There are three types of memory addresses: physical address, logical address, and relative address. Physical address is also known as absolute address, is the actual physical location of a process in main memory. This address is never directly dealt with or is not even visible to the programmer or user. The logical address is actually a reference to a memory location. This is the address generated by CPU when the program is running. So it is also known as virtual address, as it does not occur physically in memory. This address is only used as a reference to access the actual physical location of a process in memory. So there has to be a mechanism to map the logical address to corresponding physical address, and this we will discuss in the coming lecture. Another type of address is relative address. It is again a type of logical address and is expressed as a reference to some known point, such as you want to know the address of a specific instruction, for example, in your program. So you would express it in terms of some known point, like you would say how far that instruction is from start of the program. So you are actually referring to the relative address. I hope the difference among the three types of addresses must be clear to you now. Address binding is a process of mapping from one address space to another address space, such as mapping from logical address space to physical address space. Logical address space represents collection of all logical addresses within a program, while their corresponding physical address space is a collection of all physical addresses corresponding to the logical address space. User only deals with the logical addresses, which are then translated to get the physical addresses. Address binding is done at three stages. During compile time, if a user knows where his program will be loaded in main memory, so physical address is generated and is embedded with the program executable during compilation. You might have seen .exe extension files of your programs that are fast enough to be loaded in memory instead of running the whole program all again. But sometimes the executable files get crashed. That means its physical address has been occupied by another program. So you need to recompile that program and generate its executable file again so that it gets new physical address. What happens at load time? If it is not known during compile time where your program will reside in memory, so a relocatable code is generated. The loader then gets activated and translates the relocatable address to physical address. How this happens? The base address of the program in memory will be loaded to all the logical addresses by the loader in order to generate physical addresses. Now, if base address of a program is changed, so we would need to reload that program. What happens at execution time? All the instructions of the process are now in memory and are being processed by the CPU. An additional memory, if required, may be allocated, such as for linking of files, like you add header files in your code. So additional space is allocated to your program to accommodate all those header files. And or space may be deallocated from your program if your program changes memory and moves to another type of storage, such as you save your program to some disk or removable storage. So these are three different timings when your instructions are binded to memory addresses. This diagram shows the complete story we discussed in previous slide. You write your source program and compile it. Then the physical address and compile time is generated. An object code of your program is created. Then other files are linked to your code by linkage editor, such as the header files, and gets loaded in your code. So loader then will generate a relocatable address of your process, as the addresses now gets changed due to linkage of files. And at the end, executable file with extension .exe for your program will be created after connecting all the header files and allocating more memory to your program. So this all what happens to your program. As I have already said, logical address space is the collection of all logical addresses for your program. They are generated by CPU. While the physical address space is the collection of all the physical addresses corresponding to the logical address space. The physical addresses are actually located on the RAM. Logical address is visible to user, while the physical address is only visible to the memory unit, and user cannot change or reorganize them. So it may happen that logical and physical addresses remain same during compile and load time, but they will differ during the execution time definitely. So user will never know during execution time where his code will reside in main memory. So the main addresses are logical addresses and physical addresses. In coming chapter, we will discuss how logical address is translated into physical address. We have a proper mechanism for this. I hope all these types of addresses must be clear to you now. Now coming to the address translation from logical to physical address. We will also discuss this translation in virtual memory. There is a special hardware unit that ensures this translation or mapping, and this unit is known as Memory Management Unit. How this unit works? As we said earlier, translation is done by adding the contents of base register. Base register is also known as relocation register, with all the logical addresses generated by CPU. If you remember, in protection, we said base register and limit register is used to define the boundary for a process. So we are referring to the same base register here. This process will generate the actual physical addresses for your program. They are now not visible to the user, as user can only see the logical addresses. This is the example and step-by-step translation process. When a process starts execution, the base register, also known as relocation register, gets loaded with the starting address of the process, while the limit register, which also helps in the protection of the process, gets loaded with the ending physical address of the process. So whenever a logical address is generated by CPU, It is added with the contents of the base register in order to get the actual physical address, and then it is compared with the contents of the base register in order to confirm that addresses do not go beyond the process address space. So here protection is also ensured. Here is the diagrammatic depiction of how memory management unit works, as we mentioned in previous slide. CPU generates logical address of one instruction or data within the process. For example, CPU generates 346 as an address for a single instruction. Then the memory management unit gets activated, which has the information of the base register for the process. Memory management unit adds the logical address to the contents of the base register, and here the content of base register for the specific process is 14,000, for example, and the resulting actual physical address becomes 14,346 for one single instruction within the process. And this is the address where this specific instruction is stored in RAM. Another diagram showing same procedure, also highlighting the protection. Two registers are assigned to every process in memory, base and bound registers, or limit register you can say. Base register holds the starting address of the process in memory, and it is the physical address that is stored in base register, while the bound or limit register holds the ending physical address of the process in memory. CPU generates logical or relative address, which is added to the address stored in base register and then compared with the address stored in the limit or bound register by memory management unit. The corresponding physical address for the logical address is generated in this process, and this process continues for all the logical addresses generated by the CPU for a single program. If the added address goes out of bound to the address stored in the bound or limit register, so an interrupt is generated to operating system to let it know that the process is trying to access address of another process, and this is the violation of protection rule. So that process gets terminated. That is all for now. Here we come to an end of main memory management. This is the chapter. We will continue this translation process in coming chapters. I thank you all.